Hola cakes! Welcome to another video. So in today's video, we will be discussing some more past year's questions from the topics biochemistry and techniques. I have previously made a video on the similar topics. I will link it in the description and in the I button to check those videos out. All these questions were those that I posted on my community page as well as on my Telegram group. Right now on my Telegram group, I have some amazing topics that is immunology going on, and soon I will be posting bioinformatics MCQs as well. So if you want to attempt those first and then see the solutions here, please rush to the Telegram group. And without much further ado, let me get right into this video. Before I get on to this video, I would definitely like to thank these beautiful people for commenting down in my videos and giving me new and new topics to make videos on. So thank you guys and keep commenting. Now, let us move on to the first question. So this is a question that actually comes hand in hand with the pedigree analysis. So this is based on the Lord score. Now, there was a linkage analysis that was performed in a large family with an autosomal dominant hemolytic anemia using a polymorphic marker within the beta globin locus. The Lord score at the locus Q equal to 0 is negative infinity. The Lord score at Q equal to 0.01 is minus 4.5. Now, basically, what is this Q? Q is actually the one of the arm of the chromosome, right? So this specifies the position. So at that position, the correlation, the Lord score is minus 4.5. They're asking you to conclude something about the disorder. So whether the disorder is because of a gene mutation or it is not because of a gene mutation, is it because, is it an acquired syndrome or not? So to understand anything about this, you need to understand the Lord score. Now, what is Lord score? The full form is actually log of odd. That is the full form of log of odd. Okay, now what does the log of odd score tell you? It helps you to understand whether a gene is linked to a particular disorder or a particular trait or not. So it helps you to understand whether the trait you are talking about is linked or not. This is applied in a pedigree as well. Okay, so how to calculate this? The formula is log odd is equal to PL upon PI. What is PL? PL is the probability of linkage divided by the probability of independent assortment. Either it will be linked, the trait will be linked, or it will be independently assorted. Now, for an example, I can give you, like say suppose you have black eyes and curly hair. Okay, now in a suppose in a family of say 20 people, you are seeing that 15 people have black eye and curly hair. You may have a doubt that maybe black eye and curly hair are linked genes and therefore are inherited together. But how do you actually confirm whether this is true or not? So this can be done actually by the Lord score. So to see if two things are linked or they are independently assorted, you will be performing this. Now you've understood how to remove the ratio. Now once you remove the ratio, you will get some value. So now if your Lord score, okay, is more than 3, that is it is greater than 3, then you can say that there is a linkage, that those two genes are linked. But if it is less than 3, the score after calculating the probability of linkage and independent assortment, if you find that it is less than 3, that means that the genes were independently assorted and they are not linked. Okay, now in this case, see, they are telling you the Lord score is minus 4.5. So that is definitely less than 3. Less than 3 means that this particular beta locus is not actually related to the autosomal dominant hemolytic anemia. So it is not due to the beta globin gene mutation. How did we come to know? Because the Lord score is less than 3. Less than 3 score means that these two are independently assorted. They are not linked to each other. If you had a score that was say 4 plus 4.5, then you would have said that it is due to the beta globin gene that they are suffering from the autosomal dominant hemolytic anemia. So this is how you use Lord score to compare. Okay. Now let's move on to the next question. This is another very interesting question that has been asked a number of times. So the question is, a 2 kb insert has to be ligated to a 8 kb plasmid. So insert 2 kb, it has to be ligated to a 8 kb plasmid in a ligation mix where we want to keep the vector insert molar ratio 1:2. If 1 microgram of the vector is used, the amount of insert to be used is how much? So now there is a question which is put up like this. Most of the time, many of you may not have been able to answer this. And you won't believe it that it's a very, very simple question to answer. All you need to know is the formula. So I'll write down the formula over here. So to calculate the amount of insert in nanogram, the formula is nanogram of insert is equal to nanogram of vector into kb size of insert divided by kb size of vector into molar amount of insert divided by molar amount of vector. I'll repeat once again. So to calculate the nanogram of insert, okay, that is in short the amount of insert, the formula is the vector amount, which has to be in nanogram, into the kb size of insert, meaning the size of the insert in kb, divided by size of vector again in kb, into molar amount of insert upon molar amount of volume. Usually this parameter is given as a ratio. Okay, now let us simply substitute our values and find our answer. So for this, what information we have? Now this is something that we want to find, that is the amount of insert. So this answer, whatever you get, would be nanogram. That is nanogram of vector. Amount of vector here, it is given 1 microgram of vector is used. So 1 microgram, if you have to convert micro to nano, you will multiply by 10 raised to minus 3, right? It is a smaller unit. So 10 raised to minus 3, this would be nanograms into kb of insert. So insert is 2 kb given over here. So into 2 divided by kb of vector. Vector meaning the plasmid over here. So that is coming to 8 kb into molar amount of insert is to plasmid. But here, mind you, they have given you vector is to insert. You want insert is to vector. So it won't be 1:2, it will be 2:1. So just be careful of what is given in the question. So now this is 4 and this is 8. So 4 2s are 8, right? And then you have 1 divided by 2, that is coming to 0.5 into 10 raised to minus 3. Now this answer is in nanogram because you converted, right? So now here all the answers are in microgram. So to reconvert, it will just be multiplied by 10 raised to 3 and that comes out to be 0.5 microgram. So the insert amount of insert in microgram is 0.5. That is our option C. Isn't it very simple? So all you need to do is just remember this one formula. Moving on to the next one. This is again a very commonly asked question and super easy. Which one of the following result is expected when a mammalian cell in the S phase is fused with another in the G2 phase? Now these experiments are very, very common and these are called as the fusion experiments. Okay, these experiments were carried out by the scientists Rao and Johnson. Now what did they do in such kind of experiments? So they took different combinations, like one cell which is in the S phase, they fused it to another cell in the G1 phase. Then the second instance, one cell is in the M phase, the other one is in the G1 phase. Next case, one cell is in the G1 phase, the other in the G2 phase. Next instance that they did was one cell in the S phase, the other in the G2 phase. And they actually seen that which stage is the fused cell in. Okay, so in the first case, when they fused a S cell, okay, a S phase cell with a G1 phase cell, what they found was that the G1 phase, okay, sorry, the S phase got activated in both. That means that the cell which was in the G1 phase has also moved from the G1 to S phase. Now, why did this happen? Because this cell which was already in the S phase had activated cyclin A and CDK2. And this activated cyclin A and CDK2 helped this G1 phase to also move into the S phase. So therefore, S phase was activated in both. Now, the cell which was fused with the G1, the M phase cell which was fused with the G1 also moved to the M phase. So M phase was activated in both. Now, again, the reason was that in this M phase cell, it already had the MPF, that is the mitosis promoting factor, which is made up of cyclin B and CDK1. So you have activated cyclin B and CDK1. So this activated complex thus pushes this cell in the G1 also to go to M phase. Then when they fused the G1 to G2 phase, the cells remained same. There was no difference. This was still in the G1, this was still into the G2 because none of them had any activating factors. When the cell that was in the S phase was fused with the cell in the G2 phase, it still remained the same. So now in our scenario, what they have asked is a cell which was in the S phase is fused with another cell in the G2 phase. So what will happen? It says G2 phase nucleus will wait for the S phase nucleus to complete the replication and both simultaneously enter into M. That is not what happens because they don't have activating factors. They don't have the MPF. They need cyclin B and CDK1 to move ahead. S phase nucleus would immediately enter into the G2 phase without completing replication phase. This is also incorrect. Both nuclei will follow their corresponding cell cycle without influencing each other. This is absolutely correct. Due to the influence of S phase promoting factor, G2 phase cell nucleus will also end into S phase. That is also not true because this has already completed its S phase. So it can't go reverse, right? So the correct option is C, that both nuclei would follow the corresponding cycle. Very simple, just remember these 4 instances and you will be sorted out. Now, the next question is actually based on FACS, that is flow cytometry or fluorescence assisted cell sorting. These kind of questions are also very, very commonly asked. Now, what is it that you are seeing in the graph? Once you understand that, it will be very, very easy to understand. So for a typical cell, you will find this kind of FACS like this, okay, where on the y-axis, it is the number of cells and it's on the x-axis, it's the content. Okay, so here, this first peak that you see, it resembles the G1 phase. Why G1 phase? Because if you look at it, here the content is only 2C. Okay, it's not replicated yet. It's in the starting phase of the cell cycle. So it is like 2N. Correct? We say no, it's 2N. Now, the next after G1, it goes to S. Now, as you can see, S is kind of a range. It is between this 2C to 4C. So this is the phase where there is synthesis going on, replication going on. So the cells in the S phase will have anywhere between 2C to 4C. And finally, here is your G2 to M, where the cells have, are completed with G2 and are going to M, or either in G2 or M. There's no way of understanding which exactly, because once it's in crossed its S phase, it has 2N number of it has 4C, right? So therefore, this is how a typical FACS looks like. So in the G1, it is 2C. In the S, it's anywhere between 2C to 4C, and in the G2 and M, it is 4C. Okay, so now you can easily understand what is happening over here. So here in this question, they have said asynchronous animal cells were stained, were stained with a fluorescent dye binding to DNA and analyzed by flow cytometry. Asynchronous animal cells means they were all in the different phases of the cell cycle. Okay. The histogram of cell count versus fluorescence intensity. Fluorescence intensity here is nothing but the DNA content that is present. is shown in below with and without treatment. Now, since the cells were in the asynchronous phase, you can see in the untreated, you have cells in all places. Like majority of the cells, as you can see, are in the G1 phase. How do I understand majority? See, because the height corresponds to the cell count. So higher the peak means higher number of cells. Okay. The width is the content of DNA. So maximum cells are in the G1 phase. A few of them right here are in the S phase, and these cells are in the G2 or M phase. In the treated one, as you can see, there are majority of the cells in the G2 to M. You can see there are practically no cells in the G1 phase. So now what must have happened? When you treated this, these cells which were in this G1 stage, when you treated it with the whatever the treatment agent was, say X, what happened is that the G1 cells, they are not going to stay in G1 forever, right? They will progress from G1 to the S and from S to the G2. Correct. Now, they would go from G1 to S, they will go from S to G2. In this second scenario, what we can see is that G1 has no peak, which you can explain like G1 cells would have gone to S. So this progression was happening. That's how the number of cells in the G2M increased. Na? See, initially in the first panel, the cells in the G2M are very low. So because some of these G1 cells were able to go to G2, therefore you are finding maximum number of cells in G2 phase. So what does that mean? That the cells easily went from the G1 to S and from the S to G2. Therefore, even after treatment, you are seeing a number of cells in the G2. But if this G2M cells were fine, then after that, what will happen? It will again go to the G1. But as you can see, this shows no peak in the G1. Means what? That whatever this agent is, it is not allowing the cells to go from G1 to G2M to G1 phase, right? So, which answer is correct? The treatment inhibits the cell from entering S phase. Absolutely incorrect. They have gone to the S phase and that's how they have reached to G2M. The treatment increases the proportions of cells in the G1 phase. That's incorrect. We know that the cells in the G1 phase are very, very low. The treatment increases the proportion of G2 to M phase cells. Absolutely correct. We can see that the treatment increases the proportion of S phase. Okay, that is also incorrect. So our option correct is C. Now this was a very, very easy question where they were concluding just based on what you can see. You just needed to know which peak corresponds to G1, which to S and which to G2. But a more tougher question would have been that, after treatment, tell which this drug inhibited which phase. So then for that, your correct answer would have been that it was inhibiting the G2M to G1 transition. Okay. Chalo. Let's move on to the next one. Again, a very, very interesting question. An isozyme may be a monomer, dimer, or multimer with identical or distinct subunits. Following picture depicts a native page profile of the isozyme from the diploid plant. So this is a plant, and this is a first parent P1. This is a second parent P2, and this is F1. Okay, from this band, we have to conclude whether the enzyme is a monomer, homodimer, homotrimer, or pentamer. Now, to understand anything about this question, I want you to understand about isozymes. So, what are isozymes? Isozymes are nothing but enzymes that catalyze the same reaction. These enzymes, however, might, they have a different Km value, a different Vmax value, and different locations. So different parameters and different locations. Okay. But however, they catalyze the same reaction. In humans, we have a very special enzyme that is a lactate dehydrogenase, which is a 4 subunit enzyme that have different locations, like a different one in the heart, a different one in the muscles, etc. So similar condition here, we have this isozyme that they have given, and they have told us to try and identify, what kind of structure it is. So see, if an isozyme is a monomer, that is, it has only one subunit, one of the parent would have that one subunit, the other parent would have another subunit. Let us consider both have different subunits of the enzyme. So this is one subunit that is coming from the first parent. This is the other one that is coming from the second parent, right? Now, the progeny would have some of those that have come from the first parent, some of those that have come from the second parent. Now, they are just made up of one subunit. So here you can see it is one subunit. Here you can see it's one subunit. And here also it is one only subunit, right? This one and this one. It's a monomer. Now a dimer is two subunits. So in one parent, the enzyme would have been made of this A1, A1. Okay. This, let's say the parent is made up of B1, B1. Now in the progeny, there is an option. Either it can be same as the parent like A1, A1, or it can be same as the other parent B1, B1, or it can be a combination A1, B1, correct? So see, if it is a dimer, you will have three different possibilities. Either it will be one same as that of the first parent, or one same as the second parent, or it can be a mixture of the two. So if you have three bands in the progeny, it means that there are two subunits. Let's make the idea even more clear with the next one. Say now it's a tetramer, that is four subunits. So say the parent one has A1, A1, A1. The parent two has B1, 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 B1. Okay. Now the progeny can either have the parental combination, that is all A1, or all B1. But it also can have other combinations, like three subunits from the first parent, that is A1 three times and B1 once, or it can have A1 twice and B1 twice, or it can have A1 once and B1 thrice. So if it's a tetramer, you would have 5 different bands for the progeny. Now this same logic, if you apply over here, you'll get the answer. So see, the parent one, let's consider is A1, A1. The parent two is B1, B1. Now, in the progeny, you have the same band as the first parent A1, A1, same band as the second parent B1, B1. But there is another band. And what is that other band corresponding to? It must be A1, B1. So what does this indicate? It indicates that the enzyme is a homodimer, as we did over here. See, there are three bands in the progeny. So it has two subunits means dimer. The homodimer, why? Because here anyways they are running on native page. So just one subunit you will be able to come to know. Okay. So simple as that. Just remember this chart is very, very helpful. If you find two bands in the progeny, then it's a monomer. If there are three bands, it's a dimer. If there are five bands, then it's a tetramer, right? So let's move on to the next question. For the pedigree depicted below, which mode of inheritance cannot be possible? Okay, you have to see cannot be possible. Now, one very, very easy way to determine is just look at if any generation is being skipped or not skipped. If a generation is not skipped, okay, that means that that particular trait is dominant, and you will have either an autosomal dominant or an X-linked dominant. Now, as you can see, for skipping or not, you should check the parents. Now, see, in this condition, this pedigree, one of the parent has the disease trait. So, see, at least one of the progeny has. Similarly, here one parent has, so at least one progeny has. One parent has means at least one progeny has. So, straight away, we can conclude that this trait is a dominant trait. So, by default, your X-linked dominant and autosomal dominant will definitely be possible. So you don't even have to check for that. Anyways, they're asking you not possible, right? So these two are definitely possible. You can try it with the original method, like for a dominant, at least this has to be a capital A, small a, or it could be capital A, capital A. And this will always be small if it's a dominant trait, autosomal dominant. And one of the progeny has to be. So it will satisfy the requirement. So therefore, it's definitely a autosomal dominant. And you will see it's the X-linked dominant also. Now, what you need to choose is between the X-linked recessive and the autosomal recessive. Now, always choose the smallest pedigree here because it's easier to analyze. Now, when we say X-linked recessive means what? To be diseased, both the alleles must be diseased, right? So X-linked disease means that this daughter should have both X's that are diseased. So it should be XC, XC. Now, in males, you don't have any other X. So if it is disease, that particular X has to be C. Now, since this male is not disease, it must have a normal X. So if you see the progeny, it will be XC, XC, this XY. So it will be XCX, XCY, XCX, and XCY. See, if you look at it carefully, this couple will always and always have a son who is diseased. There is no way possible that with this combination you will have a non-diseased son, and there is no other possibility for the parents, right? So as you can see, out of two sons, one son is normal. This one is diseased, but this is normal. In this scenario, normal is not possible. So the pedigree cannot be an X-linked recessive. This is my correct answer. It cannot be X-linked recessive. Simple as that. Doesn't take the time at all. Now again, another interesting question. A 20-mer peptide composed of all 20 coded strand amino acids was hydrolyzed with 6 normal HCl. However, only 17 were detected by chromatography. The 3 missing amino acids are. This is more like a knowledge-based question. They are telling you that there were 20 amino acids and they treated this polypeptide with 6 normal HCl and they could only detect 17 amino acids. So the 3 amino acids went missing. Now, which are these 3 amino acids? So the 3 amino acids are actually asparagine, glutamine, and it is tryptophan. Okay, asparagine, glutamine, and tryptophan. Now, why these amino acids specifically? Because when you treat it with 6 normal HCl, aspartic acid and glutamic acid get converted into the corresponding amino acid, that is asparagine gets converted into aspartic acid and glutamine gets converted into glutamic acid. So you don't detect them as asparagine and glutamine, rather they get mixed with the aspartic acid and glutamic acid. Whereas the tryptophan is completely destroyed by the 6 normal HCl and therefore it's not detected at all. So your correct option is glutamine, aspartate, and tryptophan. Okay, sure. Next question. This is one from biochemistry. Basically a logic-based question. So the question says that in an enzyme assay, the corrected absorbance reading obtained on addition of 100 microliter of an enzyme extract is 0.025. So absorbance of 100 microliter of enzyme found out to be 0.025. Given that 1 unit of enzyme is the amount of enzyme required to increase the absorbance by 0.01 unit under assay conditions, the activity in units per ml will be dash. So by looking at the unit of what is required, you'll understand units per ml. So you need ml and you need units. Now the only place they are telling you a volume is over here, that is 100 microliter. Now how much is 100 microliter in ml? 100 microliter is how many ml? So you know that 1000 microliter is 1 ml. So 100 microliter will be actually 0.1 ml or it will be 10 raised to minus 1, right? Now, they are telling you that 1 unit corresponds to 0.001 absorbance. So they have already given you the absorbance of 100 microliter. It is 0.025 absorbance. So how many units does that correspond to? X. So X will be equal to 0.025 divided by 0.001. That is nothing but 25. Now, the enzyme activity is the absorbance units divided by the volume. So absorbing unit is 25 units and volume is 10 raised to minus 1. That comes out to be 250. The enzyme activity is 250. Very, very simple. So that's all for the MCQs. I hope this was helpful. Next up, I will be doing some MCQs related to COD and POD. If you want me to do any other specific topics, please do let me know in the comment section down below. I'll be waiting to read your comments. If you like this, please like the video, subscribe to my channel, and do join my Telegram group. So that's it for me for today. I'll see you in my next video. Bye.